Usually when we talk about a medical diagnosis, there is this expectation of precision, like engineering almost.
Right, like a broken bone or something.
Yeah, exactly. You break your arm, the x-ray shows that jagged white line, and the doctor just points at it and says, there it is.
Right. It is a very comforting binary. I mean, it's either broken or not broken. It is visible, it is categorized, and, there is a clear protocol for how to fix it.
But then you step into the world of things like neurodevelopment or trauma or, systemic autoimmune issues, and suddenly that x-ray machine is just totally useless.
Oh, yeah. Completely.
We were looking at a diagnostic landscape that is, well, honestly, it is murky. You are looking at interconnected systems, cascading effects, and shadows of symptoms where the actual root cause is hidden like 3 layers deep.
It really becomes the absolute definition of diagnostic muddy waters. You aren't looking for a single break anymore. You are looking for a pattern of resonance across a whole network of behaviors.
Exactly. And today, we are taking you, the listener, on a deep dive into an engineering landscape that is just as murky, just as wild, and honestly kind of mind-bending.
Yeah, it really is.
So whether you are prepping for a highly technical architecture meeting or trying to catch up on the bleeding edge of distributed AI systems, or if you are just insanely curious about how the internet is being rewired right under our noses, you are in the right place.
Because to figure out how they are doing this, we are looking at a really bizarre stack of internal blueprints.
Yeah, the sources for this one are wild.
They are. I mean, some of them read like standard server specs, but others, like this one ominously called the Devs Contract, read like a philosophical manifesto.
It's so strange. We're looking at a system that completely defies how traditional software engineering works.
Totally. We are looking at an architecture that treats computer code less like a list of instructions and more like a multidimensional topological organism.
It is absolutely fascinating. So the source material we have today includes an internal architecture document, simply named architecture.md.
Right. We also have that mysterious integration contract you mentioned called deathscontract.md, and finally, a project manifesto, the README.md.
And all of these documents, they detail one highly specific, highly constrained mission, which is serving an AI model called Qwen 7B.
Right. Now, before we even get into the weeds of how they are doing this, we need to establish the baseline, because Qwen 7B is a 7 billion parameter artificial intelligence model.
Right.
And from my understanding of how AI works right now, running a 7 billion parameter model is like heavy-duty industrial work.
That is the perfect place to start. Because to understand the madness of this architecture, you have to understand what the standard alternative is.
Okay, so what is the standard?
Normally, if you or a company wants to run a 7 billion parameter model like Qwen or Llama or any of these large language models, you deploy it on a massive server rack.
You are renting something like an NVIDIA H100 GPU, a graphical processing unit that costs tens of thousands of dollars, draws a massive amount of electricity, and has gigabytes upon gigabytes of dedicated video RAM or VRAM.
Right, because all those parameters, the 7 billion little mathematical weights that make up the AI's brain, they all have to be loaded into memory at the exact same time for the AI to process a single question and give you an answer.
Exactly. I mean, even if you compress the model, you are usually looking at needing roughly 4 to 8 gigabytes of high-speed memory just to hold the model. Plus more memory to handle the actual context of the conversation. It requires centralized brute force computing power.
But that is not what is happening here, and this is the core of our deep dive today. Our mission isn't just to read through technical specs.
Right, no.
It is to uncover the fascinating, wildly esoteric, and sometimes brutal engineering required to run this massive AI across a distributed, globally scattered edge network.
Specifically, the documents detail that they are running this entire operation on Cloudflare workers and durable objects.
Which turns the traditional model completely upside down, right?
Oh, entirely. Cloudflare is an edge network. It is designed to put tiny, lightweight pieces of code as physically close to the end user as possible.
Like geographic proximity.
Exactly. If you are in Tokyo, you hit a server in Tokyo. If you are in London, you hit a server in London.
And a Cloudflare worker is the vehicle for that. It is essentially a tiny ephemeral piece of code. It wakes up, handles a web request in a few milliseconds, and then just shuts back down.
Right.
It is brilliant for routing traffic or adding a quick security check to a website, but it is not a supercomputer.
Not even close. Lightweight is the absolute governing law here, and this is the physical constraint that dictates the entire architecture of this system, which brings us to honestly the most staggering number in this whole document.
Okay, let's hear it.
A Cloudflare worker has a strict non-negotiable RAM budget per request, 128 megabytes.
128 megabytes. That is it.
That is the hard ceiling.
To put that in perspective for you, a single tab open in your web browser, right now just reading a news article or looking at an image, is probably using significantly more than 128 megabytes of RAM.
Oh, easily. A standard smartphone today has 8 gigabytes of RAM. 128 megabytes is an incredibly tight, suffocating box for modern computing.
And they're trying to shove a 7 billion parameter AI model into that box. Let's ground this with some numbers from the source documents because it's wild.
Yeah, let's look at the embedding table.
Right. The embedding table for this model, which is just the dictionary part that translates the input tokens into numbers, specifically a file called token.num is around 306 megabytes.
Which is already way over the limit.
Exactly. And that is after it has been heavily compressed or quantized into a format called Q4K.
We should probably unpack what that means because quantization is the first line of defense in this architecture.
Okay, yeah, go for it.
When an AI is trained, its parameters are usually stored as high-precision floating point numbers. Think of a number with a very long decimal, like 3.14159.265, and so on. That takes up 16 or 32 bits of space per single number.
So very precise, but very bulky.
Right. Quantization is a mathematical compression technique. Q4K specifically means they are crunching those highly precise number down into 4-bit approximations.
Got it.
They are rounding them off and grouping them into blocks to save space. It introduces a tiny bit of error, but it drastically reduces the file size.
But even after doing that extreme compression, just the dictionary the AI uses to understand words is 306 megabytes.
Right.
That is more than twice the size of the entire 128 megabyte memory budget for the worker. And that is before you even load the actual brain of the AI.
Exactly. The layers, the attention mechanism.
Right. The memory needed to process whatever prompt you just typed in. It sounds physically impossible. It is like trying to sit a gallon of water into a shot glass.
It does sound impossible. But the architecture document outlines a highly formal, incredibly aggressive strategy to handle this tiny environment. They call it the fluid memory invariant.
The fluid memory invariant. Okay, that sounds like a term out of theoretical physics.
It really does.
I am going to try and visualize this for a second. Imagine you were trying to cook a massive multi-course banquet. You've got an incredibly complex recipe, thousands of ingredients.
Okay, I'm with you.
But your kitchen is in a tiny studio apartment. In fact, your counter space is so incredibly small that you can only fit one single ingredient on it at any given time.
Oh, man.
If you want to chop an onion, you have to take the carrots off the counter and put them back in the fridge. You physically cannot have two things out at once.
That is a brilliant analogy because in this system, the counter space is that 128 megabyte RAM limit.
Right.
And the ingredients are the massive blocks of data called tensors that make up the AI's layers. The fluid memory invariant states a strict rule.
Which is?
No worker holds more than the bytes for a single phase of a single layer at any point during forward inference.
So wait, I understand that an AI like Qwen Coder 7b is made up of sequential layers. Data passes through layer 1, then does some math, then passes to layer 2, all the way to the end.
Right.
The document says this model has 28 layers. So you're saying they load layer 1, do the math, and then throw layer 1 out of memory completely.
It is even more granular than that. The invariant dictates that even a single layer is broken down into distinct computational phases.
Okay.
These massive tensors are never just sitting around in memory. They are loaded into the WebAssembly or WASM linear memory immediately before the calculation that needs them.
WASM being the low-level execution environment running inside the Cloudflare worker that actually does the heavy mathematical lifting.
Yes. WASM gives them near-native execution speed. So they load the tensor from a cache into the WASM memory, do the matrix multiplication, and the absolute millisecond that calculation is done,
They evict it.
that tensor is evicted, deleted, cleared out of the RAM.
So going back to our tiny kitchen, you open the fridge, grab the onion, chop it, and you don't even set the rest of the onion down. You instantly throw it back in the fridge before you even reach for the garlic.
Constantly.
You are constantly opening and closing the fridge.
Constantly. The math on this eviction cycle is staggering. The architecture document lays it out clearly. There are 4 distinct phases per layer.
Okay, 4 phases.
The cluster itself is geographically or topologically split into 2 what they call layer stations, each handling exactly 14 layers.
So if you have 4 phases per layer and 14 layers per station, that equals 56 distinct load and evict cycles per forward pass of the AI.
56 times per request.
56 times. They are swapping massive chunks of data in and out of that tiny 128 megabyte RAM budget. That sounds exhausting for the system. I would imagine the overhead of just moving that much data around would slow everything down to a crawl.
It would if they weren't utilizing incredibly fast local caching, which we will get to in a bit. But what is terrifying is that even with this hyper-aggressive 56 times a second constant swapping, they still almost hit the absolute ceiling of the worker's memory.
Wait, really? Even after all that slicing?
Yes. The document specifically highlights a major bottleneck in the feed-forward network, or FFN.
The FFN. This is a component inside each of the 28 layers. Right? Like a place where the neural network basically reflects on the patterns it just found and projects them forward.
Exactly. And within the FFN of this specific Qwen model, there are 2 distinct, heavy mathematical operations, the gate projection and the up projection.
Okay.
The document refers to them as the forward range F gate chunk and the forward range F nub chunk.
Okay, so we have the gate and the up projection. How big are they?
At the Q4K compression level we talked about earlier, each of those projections is roughly 50 megabytes.
50 megabytes each. So mathematically, if you load them both onto the counter at the same time to do the FFN calculation, that is 100 megabytes.
And 100 megabytes sounds like it easily fits under the 128 megabyte ceiling, right? You still have 28 megabytes left over.
Right. I mean, it seems like a comfortable margin.
But it is an illusion.
Yeah.
Because you have to account for the overhead of simply running the program.
Right.
The document breaks down the total resident weight mid-forward pass. You have a resident floor of about 6 megabytes. This is for the small tensors, the normalizations, the basic program logic that always has to be there just to keep the lights on.
Okay, so the kitchen utensils that never leave the counter. So that is 6 megabytes.
Then you have the activations. This is the actual user data moving through the model, the question the user asked, and the internal representations the AI is generating.
Right.
For a standard 512 token prompt, maybe like a paragraph of text, those activations take up another 7 megabytes.
Okay, so let's do the math. If you loaded both the 50 megabyte gate projection and the 50 megabyte up projection, you'd be at 100.
Right.
Plus the 6 megabyte floor, plus the 7 megabyte activations.
Yeah.
That puts you at 113 megabytes.
113 megabytes out of 128 megabyte hard limit,
Wow.
which is terrifyingly close to the ceiling. In a managed memory environment like JavaScript, which wraps the WebAssembly in a Cloudflare worker, you do not have perfect instantaneous control over when memory is free.
No, because of the garbage collector.
Exactly. The garbage collector might take a few milliseconds too long to clean up, or the memory might fragment.
And if you spike over 128 megabytes for even a microsecond,
Boom! The worker is killed by the host environment. A hard crash. Out of memory. The user gets an error, and the whole process dies.
that is way too close for comfort.
Yeah.
So what is their solution? How do they avoid that 113 megabyte danger zone?
They split them. The architecture explicitly notes that they separate the execution of the gate chunk from the up chunk. They do not let them exist in memory at the same time.
Oh, I see.
They load the 50 megabyte gate projection, do the math, save the intermediate result, and then ruthlessly evict the gate projection. Only then do they load the 50 megabyte up projection to finish the math.
So by splitting that one specific phase into 2 subphases, the maximum resident memory at any given time is 50 for the projection, plus 6 for the floor, plus 7 for the activations.
Right.
That equals 63 megabytes.
Exactly, 63 megabytes. That cuts their memory footprint almost in half and gives them a very, very comfortable buffer below the 128 megabyte ceiling.
That's smart.
It is an incredibly precise byte-level choreography of memory. They are micromanaging the exact life cycle of every single megabyte to survive on the edge.
Okay, well, the kitchen analogy makes total sense for the active calculations, the layers. You chop the onion, put it away, grab the carrots, put them away.
Right.
But that completely ignores the first problem we talked about, the dictionary. The model has to know what the words mean before it can do any math on them.
Yes, it does.
And we established that the token-emd weight file of the dictionary is 306 megabytes, all on its own.
And you can't just load a third of a dictionary to translate a sentence. You do not know what words the user is going to use. You need the whole dictionary available.
Exactly. If I ask the AI a question, it needs to translate my English words into mathematical figures it can understand.
Right.
How do they fit a 306 megabyte embedding table into a kitchen that maxes out at 128 megabytes?
They don't. They abandon the single kitchen entirely.
What do you mean?
They break the dictionary into 8 separate kitchens.
Okay, so we are moving beyond just managing memory in one worker into how they spread the model across multiple workers.
Yes.
The architecture document explains that the system topology is a fixed product of 2 pin dimensions. First, you have the layer stations we just talked about, one entry station owning layers 0 through 13, and one exit station owning layers 14 through 27.
Right, that dimension pins the computational math footprint. It handles the processing.
But the second dimension is where they solve the dictionary problem. The document outlines 8 cobordism shards that partition the vocabulary.
And this is where the engineering shifts from clever memory management into absolutely beautiful, high-level mathematics.
I'm intrigued.
Let's look at the tokenizer for Qwen Coder 7b. The tokenizer is the part of the AI that breaks raw text down into tokens, which are essentially words, parts of words, or symbols.
Right.
The vocabulary size for this model is 152,064 tokens.
So there are 152,064 distinct concepts that the AI can recognize and translate into mathematical vectors.
Precisely. Now, they take that massive list of 152,064 tokens and they slice it exactly 8 ways. 152,064 divided by 8 is exactly 18,992.
So each of these 8 cobordism shards, which are 8 completely separate cobs, Cloudflare workers running independently takes ownership of a slice of 18,992 tokens.
Yes.
Shard 1 gets tokens 0 to 18,991, Shard 2 gets the next batch, and so on. No gaps, no overlaps.
And by splitting it 8 ways, that massive 306 megabyte footprint drops drastically. 306 divided by 8 means each shard is only holding about 38 megabytes of dictionary data.
Oh, wow.
Suddenly, it easily fits inside the 128 megabyte limit.
It fits in the memory, sure. That solves the storage problem. But mechanically, how on earth do you query it?
What do you mean?
If I send a prompt like, write a Python script to sort an array, those words, Python script, sort array, are almost certainly scattered across those 8 different dictionaries in 8 different geographic locations.
Yes, they are.
How does the system stitch the translation back together without it taking forever or turning into a tangled mess of network calls?
This is the cobordism part. And the document explicitly references a deeply complex mathematical theory to explain how they do this.
Okay.
The Atiyah-Segal TQFT topological quantum field theory, cobordism merge math.
Okay, stop right there. Topological quantum field theory. I am not a theoretical physicist. What does that actually mean for the code they are writing? Because that sounds like jargon meant to intimidate people.
I know, it sounds incredibly intimidating, but the way they apply it to the code is stunningly elegant.
Okay, explain it to me.
In TQFT, a cobordism is essentially a way to describe a manifold that connects different topological spaces. In software terms, they use this concept to translate a scattered, fragmented state across multiple network nodes back into a unified, single state without complex routing logic.
Okay, I think I follow.
They execute this through an operation they call disjoint partials using the Frobenius identity.
Okay, let's translate that into concrete action.
Yeah.
Walk me through the exact path of a request.
When you, the user, send your prompt, a coordinator worker receives it. It instantly broadcasts that exact same prompt to all 8 cobordism shards simultaneously. It fans out.
All 8 shards get the full sentence.
Yes. Now, let's say your prompt contains the token for the word apple. Because the dictionary is sliced without overlapping, only one of those 8 shards actually owns the mathematical definition, the vector, for the word apple.
Let's assume shard 3 owns the token for apple. What do shards 1, 2, 4, 5, 6, 7, and 8 do when they are asked to look up a word they don't have?
This is the genius part. If a shard receives a token outside of its assigned range, it doesn't throw a not found error.
It doesn't.
No. It doesn't send back a complex JSON message saying, I don't have this token, please check another shard. It simply emits an all-zero vector, a mathematical string of literal zeros.
Oh, wow. So 7 shards send back complete mathematical silence, and shard 3 sends back the actual dense data for apple?
Exactly. The shard signal for I don't own this is just a 0 vector, and they leverage the native behavior of the programming language here. They initialize the output buffer in the worker using a standard JavaScript float32 array. By default, when you create a float32 array in memory, it is pre-filled with zeros.
So they don't even have to do anything.
Right. The engineers don't even have to write extra code or spend CPU cycles generating zeros. They just leave the buffer untouched at that specific offset if the token isn't in their range.
That is so deeply pragmatic. It saves time, it saves compute, and it's built into the language itself.
Right. And here is where the Frobenius identity comes in to merge the cobordism. The coordinator receives 8 separate arrays back from the network.
Okay.
7 of them are entirely zeros at the position for the word apple, and 1 has the rich mathematical data. How do you merge them?
I mean, I guess you just add them.
You don't write a complex sorting algorithm. You don't try to splice them together based on index IDs. You literally just add them together, element by element.
Because 0 plus 0 plus 0 plus data plus 0 is just, well, the data.
Exactly. It is pure dumb addition. You get the perfect unified embedding vector without any complex aliasing, no risk of double counting, no missing tokens.
That's amazing.
It is an element-wise addition of disjoint partials. The math naturally perfectly resolves the fragmented state.
That is so clean. I love when complex theory distills down into something as simple as basic addition.
It is really satisfying.
But let me push back on this.
Yeah.
Because if we zoom out and look at the realities of the internet, this sounds incredibly fragile.
How so?
You are relying on 8 separate Cloudflare workers scattered across the internet to perfectly return data simultaneously for every single word in a prompt.
Right.
You are doing this element-wise addition. What happens if one of those 8 shards just, I don't know, trips and falls?
Yeah.
A network timeout, a server glitch, a routing error. Does the whole math equation just blow up?
You've hit on the exact bug that they highlight in the architecture.md document. This is a known trap they fell into early on.
How?
Originally, the coordinator used a standard JavaScript command called promise.all to fan out the requests to the shards.
And for anyone who has written JavaScript, promise.all essentially says, wait for all 8 of these network calls to finish successfully.
Yeah.
And if even one of them fails, instantly fail the whole operation.
Right. It is an all-or-nothing command. So initially, if a single shard experienced a timeout or a minor network hiccup, the entire system crashed.
Wow.
The promise. All through an error, the entire pre-fill phase was poisoned, and the user got nothing.
Which is terrible for reliability on an edge network, because edge networks are inherently noisy. I mean, packets drop all the time.
But the engineers realized that the very cobordism math they were using, that Frobenius addition, actually provides a built-in escape hatch.
What is the escape hatch?
They shifted the coordinator logic from promise.all to promise.all settled.
Meaning, wait for all 8 to finish, whether they succeed or fail, and just give me whatever you manage to get.
Yes. And because of the math, this allows for incredibly graceful degradation. Think about it. If shard 3 fails completely due to a network timeout, it doesn't return anything.
Right.
The coordinator catches that failure, and instead of crashing, it simply substitutes a locally generated array of zeros for shard 3's contribution.
Wait, but if you substitute zeros, then the word apple is translated as an all-zero vector. That's mathematically incorrect.
Yeah.
The AI won't know what apple means.
It is incorrect. The model will see an all-zero embedding row for the word apple. It will essentially be a blank spot in its comprehension. But here is why it's brilliant.
Okay.
The tokens in the other 7 shards remain perfectly accurate.
Ah, I see.
The failure is highly localized. Imagine you send a whole paragraph of text. If shard 3 goes down, maybe 2 or 3 words in that paragraph turn into zeros. The AI suddenly has a momentary lapse in vocabulary.
Like a blank spot in his brain.
Exactly. But the rest of the context, the grammar, the other subjects, the verbs, is perfectly intact.
Imagine if your autocorrect on your phone didn't just guess a word, but the actual network path to the server dropped a packet, and your phone just seamlessly hallucinated around the gap based on the surrounding sentence.
Right.
That is the level of resilience they're building. The AI can probably still understand the gist of the prompt and give a completely reasonable answer. The failure isn't fatal, it degrades gracefully.
Exactly. It is treating distributed system failure not as a catastrophic software crash, but as a minor biological brain glitch that the neural network can naturally contextualize and overcome.
Okay, so the math is elegant, the fail-safes are clever. But handling data this fast across so many shards, we were talking about reading these 38 megabyte chunks and feeding them into WASM in milliseconds that requires intense caching.
Oh, absolutely.
You cannot be downloading 38 megabytes from a central database on a hard drive every single time someone asks a question. The latency would be miserable.
Absolutely not. You need the data sitting essentially right next to the processor. And that brings us to how the system actually stores and remembers all this data, which is outlined in Section 4 of the architecture doc, Cache Hierarchies.
So we're stepping into the gritty reality of edge computing here. The system uses something called durable objects, or DOs, for caching.
Right.
For the listener, a durable object in the Cloudflare ecosystem is a way to keep state-like memory or database entries around globally, tied to a specific geographic location. So all requests for a certain piece of data route to the exact same durable object, meaning the data stays warm in memory.
Right. It prevents the worker from starting from zero on every request. And what is fascinating here is that they don't just have one blanket caching strategy.
They don't.
No, they have two completely distinct cache hierarchies tailored to the specific physics of the data they are holding. One hierarchy is for the embedding rows in the cobordism shards we just talked about, and the other is for the massive layer tensors in the layer stations.
Asymmetric caching. Let's contrast them, because the logic here reveals so much about the bottlenecks.
Yeah.
Start with the cobordism cache,
Yeah.
dictionary shards.
The cobordism cache uses an L1 and L2 hierarchy, much like a traditional CPU, but it is based entirely on data format rather than pure speed.
Okay.
The L1 cache holds raw quantized bytes. Remember Q4K, the compressed numbers. These raw rows are tiny, about 2 kilobytes per row.
Okay, so L1 is the compressed, tightly packed data.
Yes. The L2 cache, on the other hand, holds dequantized, uncompressed F32 rows. These are the full 32-bit floating point numbers that the WASM engine actually needs to do the math.
Right.
Because they are uncompressed, they are much larger, about 14 kilobytes per row.
That is a massive difference in size. 14 kilobytes versus 2 kilobytes. It is 7 times larger.
Exactly. And the document explicitly explains the why behind this specific split. A durable object has its own memory budget constraint of 256 megabytes. If you try to store the uncompressed F32 rows in that 256 megabyte budget, you can only fit about 18,000 rows. You would be constantly running out of room and having to fetch data from slower storage.
But if you store the raw, compressed Q4K rows,
you can fit about 128,000 rows in that same budget.
So they are making a very conscious, calculated trade-off. They're saying RAM is our most precious commodity.
Yes.
But the compute power required to dequantize, to mathematically uncompress the data on the fly from Q4 to F32 is relatively cheap and fast.
Yes. They would much rather spend a tiny fraction of a millisecond uncompressing the data per call than run out of memory and hit a network latency wall. It's a pure optimization play.
Okay, so that is the cobordism cache. Uniform row sizes, predictable memory usage, and they use a standard LRU, least recently used, eviction policy.
Right.
Basically, if a word hasn't been looked up in a while, kick it out of the cache to make room for a new word. Simple. But the layer cache, the one holding those massive computational tensors we talked about earlier, works completely differently.
It has to, because the sizes of the tensors in the layers vary wildly. You have tiny normalization tensors that are a few kilobytes, and massive matrix multiplication tensors that are 50 megabytes.
Right.
The layer cache uses a very specific, custom, least recently used heuristic. It actively discriminates based on the type of operation. It specifically pins certain things to stay resident in memory permanently while aggressively evicting others.
What gets VIP status? What gets pinned?
Smaller things.
Yeah.
The heuristic dictates that anything under 1 megabyte stays resident. The norm tensors stay resident. The output weights stay resident.
Okay.
But the giant matmul tensors the matrix multiplication blocks, like the FFN projections we discussed, those are constantly being evicted the moment they go over budget.
I want to understand the why here. Why are norms kept, but matmul is evicted? Let's go back to the kitchen.
Okay, let's do it.
It is like saying the salt and pepper shakers, the small things, the norms, they get to stay on the counter permanently.
Mm-hmm.
But the massive turkey, the matmul tensor, goes back in the fridge the second you're done slicing it.
Mm-hmm.
But mathematically, why is that the right call?
It comes down to how a transformer neural network processes data. A matrix multiplication is a massive, heavy, linear transformation.
Right.
In a forward pass, it generally happens once sequentially at a very specific point in the layer. You do the heavy lifting, and you are done with that tensor for the rest of the pass.
So you know exactly when you need it and when you don't.
Right. But normalizations, which ensure the numbers don't spiral out of control into infinity, those might be constantly referenced across different microstages of the layer to keep the math stable.
Oh, I see.
And because they are so small, maybe just a vector of a few thousand numbers rather than a matrix of millions, the cost of evicting and reloading them repeatedly far outweighs the tiny bit of memory they consume. Pinning them to the counter is just smart engineering.
It makes total sense.
Yeah.
But navigating this hyper-specific caching logic, wrangling raw bytes on an edge network, it is incredibly fraught. In fact, this is where we find some of the most spectacular engineering traps in the entire document.
Yes. The reality of building at this level is that your bugs aren't logical errors like I forgot an if statement. Your bugs are structural physics problem.
Exactly. I've been waiting to talk about this part. Section 8 of the architecture.md is titled Recently Found and Fixed Bugs, but in parentheses, it ominously says known traps.
It is pretty bleak.
It reads like a horror story for developers.
It really does. It is left there as a stark warning to the next engineer so they don't rediscover these failure modes the hard way.
And the absolute best one, the most spectacular bug in the document, is dated April 25, 2026, the .NOT file format bug. I want us to really dig into the exact mechanism of this bug because it is the definition of a cascading silent failure. It is a nightmare.
The off-by-one lobotomy.
Yes. Okay, to set the stage, the .NOT file is the custom container format they use to store the model's weights and metadata on disk before loading it into the cache. Why build a custom format? Why not use standard AI formats?
Because standard formats aren't optimized for the extreme memory alignment needs of WebAssembly in a 128 megabyte environment.
Okay.
They needed a format where they could mathematically calculate the exact byte offset of a tensor and load it directly into WASM linear memory without parsing the whole file, so they built the .NOT format.
Okay, so the .NOT file has a header at the very beginning of the file. Inside that header is some JSON metadata. The JSON is essentially a map that tells the system, the AKFN gate tensor starts at byte 1 million, the up tensor starts at byte 2 million, and so on.
Exactly. Now, the bug occurred between the encoder, the program that creates the NOT file, and the reader, the program running on the Cloudflare worker that opens the file. The encoder accidentally padded the JSON metadata with trailing spaces.
Just empty space characters at the end of the text string. Nothing malicious, just sloppy formatting.
Right. And then it wrote the padded length of that JSON, including all those empty spaces, into the file's primary header.
Okay, so the header explicitly says the metadata is exactly this long.
But the worker program was programmed with a slightly different assumption. It assumed the length written in the header was the unpadded length of the JSON.
Oh, no. I can see where this is going.
Because of the way they calculate 4-byte memory alignment to keep WASM happy, the specific formula in the document is 10 plus Medellin plus 3 bitwise and not 3. This discrepancy between padded and unpadded length created a payload offset shift of exactly 1 byte.
One single byte. In a file that is gigabytes large containing billions of parameters, everything is shifted by one single byte.
1 byte. Now, remember the quantization we talked about earlier?
Yeah.
The Q4K format.
Yeah.
It packs the numbers very tightly into blocks of 256 elements. Because you lose precision when compressing down to 4 bits, the start of every block contains a superscale value. This is a higher precision multiplier that is absolutely crucial for mathematically decoding the 256 compressed numbers that follow it.
Right, it is the anchor. If the numbers are 1, 2, and 3, but the superscale is 100, the actual values are 100, 200, and 300.
Exactly. Because the reader was shifted by 1 byte, every single time it tried to read a Q4K block from the file, it read its data 1 byte off, it missed the correct superscale, and instead it was reading the previous block superscale values or the tail end of the compressed data.
So the multiplier was completely, fundamentally wrong for every single calculation across all 7 billion parameters.
It was entirely shifted. And what is truly terrifying about this is that it didn't cause the program to crash. It didn't throw a parsing error.
Wait, why wouldn't it crash? If the data is misaligned, shouldn't the program recognize that it is reading garbage?
Because at this low level, the program is just blindly reading bytes from memory addresses and feeding them into math functions. The WebAssembly engine doesn't know the math is wrong. It just sees binary numbers and multiplies them as instructed.
That is wild.
But the resulting numbers were absolute garbage. It silently produced massive overflow errors, resulting in NaN values, which stands for not a number in the IE floating point standard. It just output pure mathematical gibberish.
It silently lobotomized the AI. You can send a prompt asking it to code a simple HTML website, and it just spits out alien text or endless streams of punctuation because every single synapse in its simulated brain is shifted by 1 byte.
And the failure mode is so insidious. If you didn't manually check the specific payload offset values in a hex editor against the file size minus the tensor payload total, you would never know the NOT file was structurally stale. You would just think the AI was broken.
Now, that sounds miserable to debug.
Oh, it must have been. The fix was incredibly simple. Just pad the spaces after calculating the JSON length and write the unpadded length, but finding that bug must have taken weeks of agonizing debugging.
I can only imagine the debug sessions. Staring at raw binary, trying to find a missing space. And that is not even the only trap. There is another one mentioned that is just as frustrating, the tensor type versus type field name mismatch.
Ah, yes, that one. The raw not JSON metadata used the word type to define the format, but the WebAssembly backend was programmed to look for the word tensor type.
Two completely different teams writing two different parts of the stack, and a simple naming mismatch. So what happened?
The worker asked the JSON for tensor type, got an undefined response for every single entry, and instead of failing, it fell through to a default fallback behavior.
And what was the fallback behavior?
It defaulted to an all-zero F32 vector for everything. Every shard produced 0 embeddings for every token. The downstream pipeline just happily folded those 0 rows through all 28 layers.
Wow.
And because there was 0 variance in the data, the final output layer of the AI emitted a near-uniform softmax.
Okay, uniform softmax. Let's translate that for the listener. The softmax is the final step where the AI decides what word to say next. It gives a probability score to all 152,000 tokens. A high score means say this word. A uniform softmax means, well, what does it mean?
It means every single one of those 152,000 words has the exact same probability of being said. The AI has absolutely no preference. It's a completely indifferent.
Which again decodes as repetitive, random gibberish. No crash, just a zombie AI spewing random dictionary words. It is amazing how these massive, complex mathematical systems can be brought to their knees by a typo in a JSON field.
Or a missing command. There was the ctx.waitUntil trap, which is specific to the Cloudflare architecture.
Right, explain that one, because that highlights how ephemeral this environment is.
When you write data to the durable objects key value store to cache it, that write operation happens asynchronously. It takes a few milliseconds for the database to confirm the save.
Right.
If you don't explicitly use the ctx.waitUntil command to tell the Cloudflare runtime, hey, wait until this background write finishes before you shut down the worker, the runtime will just kill the isolate. The absolute millisecond the HTTP response is sent back to the user.
It doesn't care that you were in the middle of saving a file. The request is done, so it murders the process.
Exactly. Isolated teardowns silently orphaning cache writes. The cache just failed to persist, and nobody knew why because there was no error thrown. The write just vanished into the ether.
It is so gritty. It is so grounded. You are literally wrangling Section 4 of the README, the monster mesh and the philosophy of shape. This is where I just about had to sit down and read the text 3 times. The project manifesto outlines a unified, scale-invariant holographic transport and monitoring system.
Built on what they call the Gnosis formal science of the invariant law.
It sounds like science fiction. It sounds like a cult. The core mandate of this section states that they view logic, the actual code executing the AI, not as symbolic text. They view it as a topological shape, a persistent barcode. How do we even begin to unpack what that means?
It is a radical reframing of how we understand code. Normally, as a programmer, you think of execution as a 1D path. Line 1 runs, then line 2, then an if statement branches to line 5, then a loop runs 3 times.
Right.
It is a straight line of dominoes falling, occasionally branching, but always linear in time.
Right. A to B to C, it is text read from top to bottom.
But the manifoldic frame they describe in the manifesto generalizes this execution path into a multi-dimensional transport primitive. They are trying to visualize execution manifolds.
Okay, visualizing code.
They are taking that 1D path of dominoes falling and mapping it into 3D holographic states, using what they call stone space coordinates, which encode the level and phase of the logic and topological signatures.
So they are turning the abstract act of an AI computing a math problem into a three-dimensional geometric shape that they can look at.
Exactly. They are spatializing logic, and the process they use to do this is called the holographic handshake.
Okay, walk me through the holographic handshake, because the source document describes it in 3 distinct steps: capture, intersection, and resonance.
Let's start with capture. The system takes multiple 2D views from different perspectives of these logical blocks running across the network. Think of it as taking high-speed photographs of the AI's execution path from different angles in the cluster.
Okay, so you have these flat 2D snapshots of the code running.
Then comes intersection. This involves a mechanism they call the sovereign sieve. The sieve takes all those 2D views and attempts to reconstruct the 3D shape. Crucially, it discards any 3D configuration that doesn't perfectly align with every single one of those 2D views.
I want to try and visualize this for the listener because it is beautiful. It sounds like playing with shadow puppets.
Yeah, that's a good way to look at it.
Imagine you have 3 different flashlights pointing at a blank wall, and you are holding your hand up in the middle. Your hand makes 3 different 2D shadows on the wall from 3 different angles.
Right.
The sovereign sieve is like looking at those 3 shadows and using them to perfectly reverse engineer the exact 3D shape of your hand. If a theoretical 3D shape doesn't perfectly cast all three of those exact shadows simultaneously, the sieve discards it as false.
That is a brilliant analogy. That is exactly what the sovereign sieve is doing, but with mathematical state instead of light. And then step 3 is resonance. Once the sieve verifies the path, once it confirms the 3D shape is true, the logic snaps into place, rematerializing the original 3D execution manifold across the network.
It is just staggering to think about debugging code this way. You aren't reading text logs saying error on line 42. You are looking at the geometric resonance of a multidimensional shadow. And the core mandate of this entire system, the phrase repeated like a mantra in the text is, if it folds, it fits.
If it folds, it fits. It means that if the logical shape of the program can be mathematically mapped and folded into this specific topological signature, it can be transported and run anywhere on the cluster. It is completely media agnostic.
Media agnostic. The document says it supports video, audio, which they have a whole poetic section on, calling it NUMA, using foam, prosody, and residual codecs, semantic space, fingerprints, and knots. It treats all data as just shapes to be folded.
But there are strict limits. The document details the manifold-hodic frame bounds. There are specific regimes of data it absolutely cannot express.
Right, and the first bound listed is pure chaos, which they label with the term ASAT.
Pure chaos is defined in the manifesto as truly random data with zero structural recurrence. If the data has no internal patterns, if it has no holes or shapes, the sovereign sieve cannot latch onto it. You can't make a shadow puppet out of fog. The manifold collapses.
If it doesn't fold, it doesn't fit. The document literally says that any logic that refuses to return to the grounding triton, whatever that means, is violently vented from the system as bizarro noise.
Bizarro noise. It is such evocative, almost mythological language for what is fundamentally unparsable computer data.
It really is. And reading all this theory makes you wonder how these engineers actually sit down at a keyboard and write standard Rust code in this environment. Which brings us to the final document, the Death's Contract MD. This is the bridge. This connects the grand philosophical framework of the monster mesh back to the actual gritty practice of coding the nevering constraints.
The 5 deaths.
I mean, just the name, the 5 deaths. When I first read that, I thought it was going to be a post-mortem of 5 catastrophic server outages. Looking in the document, they're referring to specific Rust modules, right? What are the 5 deaths?
They are standalone files written in the Rust programming language that handle the most volatile, dangerous memory management tasks. 1 file per death. For example, death number 1 is a file called srcmat.vecmemo.rs. Based on the name, this likely handles the memoization, the caching of the massive matrix vector multiplications. Death number 2 is the amplituhedron cache.
Amplituhedron cache. The naming convention is incredibly dramatic.
It is dramatic, but the contract outlines a very strict, unbreakable rule for how these deaths are integrated into the main application logic, specifically into the core files model.rs and wasmbindings.rs.
The single author rule.
Right. It states that subagents, which, given the context of modern AI development, are highly likely to be automated. AI coding assistants working autonomously on the repository can work on these standalone death modules in parallel. They can optimize them, rewrite them, test them, but they are absolutely forbidden from integrating them. Only the foreground session, the main human developer or the primary orchestrator, is allowed to edit the integration points.
The document says, subagents that need integration time changes return text patches. The foreground applies them serially.
This is a massive defense mechanism. Think about the philosophy of the monster mesh we just discussed. They are terrified of SAT pure chaos. If you have multiple automated AI subagents concurrently writing code into the core integration files, overlapping their logic, you get merge conflicts, tangled states, nonlinear dependencies, you lose the clean 3D shape, you get chaos.
You get fog. And the manifold collapses.
Exactly. The single author rule prevents the very chaos the sovereign sieve is designed to filter out. It forces all the parallel, potentially messy, concurrent work of the AI subagents to be serialized. It acts as a funnel, cleanly folding the new logic into the main topology by one central authority.
So the strict administrative engineering rules are literally manifesting the topological philosophy. To keep the geometric shape of the code clean, to ensure it folds, they have to legally throttle the entire coding workflow into a single human bottleneck. It is just wow.
It is a remarkable synthesis of high-level theoretical philosophy and low-level practical discipline. They have built a belief system to justify their strict coding standards.
It really is. Okay, let's take a breath, step back, and summarize this incredible journey for the listener, because we have covered a massive amount of ground today.
We started with the extreme physics of the 128 megabyte worker limit. To fit a 7 billion parameter AI into a space smaller than a web browser tab, they had to slice 50 megabyte tensor chunks,
Oh.
constantly loading and evicting memory 56 times a second to respect the fluid memory invariant.
Then, to handle the massive 306 megabyte vocabulary dictionary, they split it across 8 separate network shards, relying on the elegant, esoteric math of the Tia-Segal TQFT cobordism merge to add disjoint partials together seamlessly, turning zero vectors into perfect translations.
We explored the asymmetric caching trade-offs, choosing L1 compressed memory over L2 speed. And we saw how that intricate system was incredibly vulnerable to the realities of edge computing, where a single trailing space in a custom .NOT file could shift a payload by 1 byte, misaligning the quantization superscales and silently lobotomizing the AI with NAND gibberish.
And finally, we saw how wrestling with those exact constraints, fighting the dirt and grime of memory addresses, inspired an almost spiritual, topological view of computer logic. A world where code isn't lines of text, but a 3D holographic monster mesh that must be carefully folded through a sovereign sieve to avoid collapsing into pure chaos and bizarro noise.
It is a masterclass in pushing distributed architecture to its absolute physical breaking point and then redefining the underlying math and philosophy to go even further.
It really is. And I want to leave you, the listener, with a final thought to mull over. Something that builds on all of this, but really gets to the heart of what this architecture implies about the future of computing.
Okay, I am ready.
We started this deep dive by talking about medical diagnostics, looking for the broken bone in the X-ray, looking for a physical thing in a specific place. But if an AI model is being sliced into 8 vocabulary shards, if its very brain is bouncing across multiple Cloudflare layers in different countries, constantly loading and evicting memory fractions of a second at a time, and represented not as a text file on a disk, but as a topological monster mesh shadow captured by a sovereign sea.
Where does the AI actually exist?
Exactly. In this architecture, the model isn't a single file sitting on a hard drive anymore. It is not a program running on a server rack you can point to. It is a momentary distributed event. It is a mathematical shape, briefly drawn across a global network of microscopic edge nodes, only snapping into resonance for a millisecond to answer your question before vanishing completely back into the dark.
A ghost in the global machine.
Thank you for taking this deep dive into the source material with us. Keep questioning the shape of things.